Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is how to perform instrument transformer testing with Megger MRCT instruments. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and a link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Sanket Bolar, Applications Engineer. Also, to assist with the question and answer session, we will have joining us Volny Naranjo, Senior Applications Engineer, and Daniel Carreño, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, Sanket.
Thanks, Mike. Good afternoon, everyone. Let's get started with today's presentation. Today, as Mike said, we are going to be talking about how to test instrument transformers using the MRCT. This presentation is going to be divided into 4 sections. We are going to first start off by talking a little bit about CTs, and then we're going to talk about the testing that is typically done out in the field on CTs. Then we're going to talk about the product itself, the MRCT, how to test CTs with the MRCT. And then eventually we're going to conclude the presentation by talking about the additional functionality that it has to be able to test VTs and CVTs. Okay, let's get started. So let's talk about what are current transformers. Let's start from the very basics. So current transformer is a transformer, right? It looks different, but it's essentially a transformer. And the way it functions is the CT is wrapped around a primary conductor, and when the current flows through the primary conductor, the field that is present around the current, the field that is present around the conductor, because the current that flows, that field is channeled in the core, and because of that, a voltage is induced, but because the secondary is shorted, a current flows instead through that shorted secondary circuit, and the current that flows is proportional proportional to the current that flows through a secondary depends on the ratio of the CT. So for example, if you have a CT which has a ratio of 600 by 5, then if 600 amps flows through the primary conductor, then you will have 5 amps flowing through the secondary. So it works on the ampere turns principle, which means that the number of the amps times the turns on one side is equal to the amps times the turns on the other side. So you'll have a winding with a certain number of turns on the core, on the CT core, and because of it having those number of turns, the current will be stepped down by that ratio. So if you have a 600 by 5 CT, then your winding has 120 turns, and so it's stepping it down. The primary turn is just 1, because just the primary conductor that's going through the CT. So it's 1 turn on the primary side, and then you have 120 turns on the secondary side. So the current steps down from 600 to 600 divided by 120, which is 5. Now, ideally, that's what should happen. If 600 amps flows through the primary, then you should get 5 amps on the secondary. But what happens is part of the energy that's being transferred over from the primary side to the secondary side is used up in the excitation of the core. So that results in a little bit of a percentage ratio error. So a negligible portion of the secondary current is missing, and you will not measure exactly 5 amps, but the current will be a little less than 5 amps. The portion that's missing is negligible when the CT is under normal operation, but as you move into higher currents, or as the voltage that develops across the secondary winding increases, that error increases, and that negligible portion becomes a sizable portion. That's when we say that the CT is approaching saturation. So and then that's the reason we use the term voltage limited and not voltage dependent, because the performance of the CT is limited by the voltage that develops across the CT secondary. Based on construction, the CTs can be classified into 3 types. You have a bar type construction, where the primary is in the form of a bar. You have a window type construction where the primary conductor is missing. So you have a hollow uh, donut type CT. And then you have a wound type construction where there is a primary winding and there is a secondary winding, and both are wound in the same core. Based on application, the CTs can be classified into two types: relaying or protection class, and then you have the metering class. So let's talk about these two types. Let's talk about relaying CTs first. These CTs are used in the protection systems. They serve as the eyes of the protection system. So they see the current that arises when a fault occurs, and they provide the feedback to the relay, and the relay takes appropriate action depending on the magnitude that it sees. So it's important that the CT should be reliable, should be able to measure the current with a certain degree of accuracy, even when fault occurs and the current increases to several times its rated value. The accuracy here is not the top priority, but the CT needs to have a range when it comes to needs to have a wide range when it comes to the magnitude of the current that it can reliably measure. So you will see that the accuracy limits that are provided here for C-type CT, it's 3% at rated current, and at 20 times, it still needs to have a certain degree of accuracy. So the limit that is specified at 20 times is 10%, which means that for a 600 by 5 CT, even if the current goes to 600 times 20, which is 12,000 amps, the CT should still be able to measure current to within plus minus 10% of 100 amps on the secondary, right? Which would be the number when 20 times the rated current flows through the secondary. When you look at the accuracy specifications for protection CTs, you'll typically see this. You'll see C100, C200, C400. So what does that mean? The accuracy class of a protection CT specified in terms of its secondary terminal voltage. So when it says C100, what it's saying is that 100 volts will develop across the CT when a standard burden is connected to it, and the standard burden in this case 1 ohms, and 20 times the rated current flows through it. So 20 times the rated current is 100 amps. When 100 amps flows through 1 ohm, you get 100 volts. So when that secondary terminal voltage develops across the CT, it should still be able to measure the CT ratio within an accuracy limit of plus minus 10%. So the per stage ratio error should not exceed 10%, even when you have 20 times the rated current flowing, as long as the standard burden is 1 ohms or less. So on this table, you can see what are the burden values which correspond to different types of different values of secondary terminal voltage. For a C800 CT, the burden is 8 ohms. For a C400 CT, the burden is 4 ohms. So as long as the burden connected to the CT is less than or equal to the standard burden for that particular CT, the CT should be able to function as per the specifications, and the ratio error should not exceed 10% at 20 times the rated current. Let's talk about metering CTs. Metering CTs measure load current, so they need to have a high level of accuracy. You will see that the accuracy limits specified in the standards are much less than the accuracy limits for the protection CT, or much tighter. So for a 0.3 accuracy class CT, for example, the per stage ratio error limit needs to be plus minus 0.3% at rated current. And then when you have lower current, so for any current between 100% and 10% of rated current, the error limit doubles, which is 0.6%. Now that's for 0.3 accuracy class. For 0.6, it's 0.6% at rated current and 0.12% at 100 to 10% of rated current. And then on the left here, this table shows you the different burdens. So along with the accuracy class, you will be able to see a burden value on the nameplate as well. So if it says 0.3 B 1.8, what it means is that the CT will be able to function as per its 0.3 accuracy class, as long as the burden doesn't exceed 1.8 ohms. The percentage ratio error is also represented graphically in the form of this graph. This graph basically tells us that not only is the magnitude of the error important, but we also need to look at the phase displacement. And the graph covers both. On the y-axis, you can see the magnitude error limit, and on the x-axis, you can see the phase displacement limits. So the limits are expressed in the form of a parallelogram. You can see two parallelograms. The inner one is for rated current, and the outer one is for 10% of the rated current. So when you test the CT at these two levels, you will get a data point which you can plot on this graph based on the magnitude and the phase displacement that you see for the ratio error. And the data point that you plot on the graph needs to be within the parallelogram for the corresponding current level. Okay, so that was a little bit about the theory of the CTs. Now let's talk about field testing that's done on CTs. The first test that's done on a CT out in the field is CT ratio verification or CT ratio measurement. Now, CT ratio, the factory way of measuring the CT ratio is by current injection. So they inject current through the primary and measure the secondary current, and it involves a lot of it requires a lot of accuracy. And that is needed because it's the factory testing that's being done by the CT, and you want to make sure that the CT is designed as per the specification. So a lot of emphasis is placed on accuracy. When you test out in the field, the main objective of doing this test is to verify that it meets that it is what it is. It is what it says on the nameplate. We don't care so much about accuracy. Well, we need to make sure that it's within the limits, but it doesn't need to be as accurate as it would need to be when the manufacturer is doing it out in the factory. Current injection is kind of impractical in some situations when you test on CTs on an asset. So for example, if you're testing CTs on a transformer, it's not easy to just inject hundreds of amps through a transformer to measure the CT secondary current. So typically when you test out in the field, all these portable test sets will test the ratio by secondary voltage application, which means that the voltage is applied on the secondary winding of the CT, and the voltage induced on the primary is measured. And that voltage that's induced on the primary, it will be dependent on the ratio of the CT. So if you have a 600 by 5 CT, if I apply 120 volts on the CT secondary, I should get 1 volt on the CT primary. And that's because it's essentially a transformer, right? It does step down current, but the voltage relationship should also work the same way because it's a transformer. When we do the CT ratio test, we also check the polarity of the CT. The polarity of the CT is equally important. It's important to know the ratio so that we know that the CT is performing, so that we know that we would be able to reliably measure the current that's flowing through the primary. But it's also equally important to check the polarity to make sure that there won't be any problems. For example, if you are using CTs in a differential protection scheme, and the polarity of one of your CTs is reversed, then that can result in unnecessary tripping. So your differential protection won't work right if the polarity is wrong. And that's just one example. You have to make sure that the polarity is good. And that is checked when you run the CT ratio test by looking at the phase deviation between the measured voltage and the applied voltage. If the phase deviation is 0, then you know that the polarity is correct. It's subtractive polarity. But if it's off by 180 degrees, then you know that the polarity is reversed or additive polarity. CT secondary winding resistance is also an important test because you need to measure the resistance of the secondary winding, as that's the internal resistance of the CT. The internal resistance along with the external burden influences the performance of the CT. So you want to make sure that that resistance is a low number. Now, that's one of the objectives. The other objective is, of course, to look for any damage to the winding, to look for points of loose connection. When you test CTs out in the field, you're not making the connections directly on the secondary winding. You would typically make connections on the terminal box. So you don't just test the CT secondary winding, you also test the wiring that leads up to the CT secondary winding. So any problems with that wiring, any points of loose connections, loose contacts, will show up as a high resistance value. And then you can carry out further investigation to determine where exactly lies the problem. Once this test is done, because in this test we inject DC current through the winding, we end up magnetizing the core. So it's important to demagnetize the core and restore it back to its original state. So this test is typically followed by a demagnetization process. Demagnetization is very important, and one of the reasons why it's important is because if you're going to be running a saturation test after this one, then you want to make sure that you get accurate saturation curves. If the core is magnetized when you run a saturation test on it, then you'll get skewed results. You'll see a little bit of a skewing in the lower values on the saturation curve. So what is saturation test? In the saturation test, what we do is we apply a voltage across the CT secondary winding, and we measure the current that it draws. We do this, we ramp up the voltage at a constant rate, and we observe the increase in the current. What we'll see is the response is the relationship between the voltage and current is linear. So you will see a straight line with a positive slope, but as the voltage reaches a certain value, you will see that the slope starts to become less steep and the curves start to flatten out. And at that point, we say that the core is approaching saturation. So what exactly is going on here? As I said earlier, when a CT is operational, you get a little bit of a ratio error because a certain portion of the energy is utilized in excitation of the core. And we are basically measuring that excitation current here, the current that's being used up in ensuring the flux flows through the core. And as voltage increases, the excitation current also increases, but at a certain point, the core starts to saturate. And when that happens, more and more of the energy starts getting utilized in the excitation of the core until the core is unable to keep up with the increasing voltage and the curve flattens out, which means that the core loses its inductive properties. Now, what's the objective behind doing this test? The objective is it's mainly meant for protection CTs. As I said earlier, protection CTs are meant to be able to see the current or measure the current over a wide range magnitude wise. So we want to make sure that at high fault currents, the CT core doesn't saturate and the relay would still be able to see the fault current. And for that to happen, it's important that we know that the CT core won't saturate, and we make sure of that by measuring the actual knee point voltage. So if it says that it's if it says on the specifications of the CT that it's a C400 CT, then we know that the saturation voltage would be a little less than 400, maybe around 300 volts, but we wouldn't expect the saturation voltage to be around 50 volts. If it's around 50 volts, then it's a very low number. So we would expect the saturation voltage to be a high enough number to where it's close to the secondary terminal voltage, which is mentioned on the nameplate of the CT. And the logic behind that is, if you look at the x-axis here, it says that on the x-axis you can see that the number goes all the way up to 100 amps. Here you have the number 10 on the x-axis. So 10, remember I said the error limit is 10% for 20 times the rated current, and 10% of 100 amps is 10 amps, right? So 10 amps actually corresponds to 10 amps actually corresponds to the secondary terminal voltage, which is for a C400 CT, let's say 400 volts. So if this is 400 volts, I mean, it's a different number on the graph here, but if this is 400 volts, I would expect the knee point voltage to be somewhere lower than 400 volts. Not too low, but a value which is a little bit less than 400 volts. Besides that, the excitation current test is also used for calculating the performance of the CT. And we'll talk a little bit more about that when we get to the MRCT portion and we are looking at the reports. Let's talk about insulation resistance test. In this test, we check the insulation of the wiring and the insulation of the CT by applying a DC voltage across the insulation. There are 3 different measurements that are recommended in the guide, in the IEEE guide, that deals with field testing of CTs. And what it says is you can apply a voltage between the secondary winding and ground. You can apply voltage between the primary winding and ground. You can apply voltage between the secondary to the primary. At the very least, it's important that you do secondary to primary, where you're checking the CT insulation. And then if you want to check the insulation of the wiring as well, then you can do secondary to ground. Burden is the impedance of the external circuit that's connected to the CT. So when you do a burden test, you're not actually running the test on the CT itself. You're testing the external circuit that's connected to the CT, and you measure the impedance of that circuit. This is done by injecting a current through the CT and measuring the voltage that's required to drive that current. So V by I, you get the Z, you get the impedance of the circuit, and you want to make sure that that's less than the standard burden that's specified for that particular CT. So if you're testing the burden for a metering CT and it says B 1.8, then you want to make sure that the impedance of the burden is less than 1.8 ohms. Let's get to the product now. We've talked a little bit about the theory of CTs. We talked about the different tests that are done on CTs. Now let's talk about using the MRCT to run these tests. Before we get to the testing part of it, let's talk a little bit about what the MRCT offers. Now the MRCT is Megger's premier CT test set, and it started off as just that, a CT test set. It had the insulation resistance test option. So it's if you don't want to include that in your MRCT, you can get one without that as well. But after that, we included a relay testing option. There is an SMRT one basically inside it, which enables you to use it as a single phase relay test set. We included a DC testing option later on, and then we moved into VT testing and CVT testing. So the DC testing option, the MRCT is capable of putting out up to 2 kV. Typically, you can saturate most CTs within that 2 kV range, but sometimes you can run into special applications like TPZ, TPY core CTs, which are used in generation facilities. And these CTs need a lot of voltage to saturate. So these CTs can have a really high saturation voltage. You cannot saturate those by the conventional AC excitation method. So what we use is a DC excitation method, and this is not something that we came up with. This is done as per the standards. And with this technique, you can achieve saturation of CTs which have an e-point voltage of up to 30 kV. So if you deal with these kinds of CTs a lot and you want to use the MRCT to test these CTs, you can get the DC testing option, and with that you would be able to test those CTs. Relay testing option, as I mentioned earlier, it's basically an SMRT1 that's provided inside the MRCT, a single phase relay test set, and if you want to use it as one, you can go ahead and get this option. VT testing option is for inductive voltage transformers, and it has 2 types. It has the basic version, which with which you can measure the ratio and you can measure the secondary winding resistance. With the advanced version, you can measure the excitation current and the short circuit impedance. The point of running the advanced test is it helps you calculate the performance of the VT, just as we calculate the performance of the CT when we run all of those tests on a CT. With the CVT testing option, at the moment we offer the basic version with which you can measure the ratio, and at some point we will be adding to it, we'll be offering advanced tests just like we do for the inductive voltage transformers as well. So when we look at the data sheet, if you're looking to purchase one, you will see this page on the data sheet, and basically it tells you about all these options, and you based on the options that you want, you come up with this configuration and you provide it to us. and we'll provide the right product to you. So it's important that you go over these and determine what exactly you need and what you don't, and based on that you you get a quote from us. Okay, so now once you get your MRCT, when you start the PowerDB software, you will see on the toolbar it says Tools. Under Tools, you will see a checkbox that says Enable Driver Log. I would recommend that you check that box. Now, with that box checked, basically what the software does is it creates a log of all your measurements. Now, when you're out in the field, if you run into some odd values, you want to reach out to us. When you give us a call, we may ask you for this measurement, and that basically helps us see what exactly where you're doing without us having to ask you to replicate those measurements, spend more time. So it just makes it easier for us to help you. So just enable this driver logging, and all of that information on your measurements will be stored, and we can basically see uh, what was being done, what tests were being done with the instrument when we try to help you out. Connecting to the MRCT is pretty simple. It's done using an Ethernet cable. There is an Ethernet port on the MRCT which says out or PC. You'll just connect to that Ethernet port, and you will be able to connect to the instrument. This is the light version. This is what the light PowerDB Lite version looks like. So when you start the software, what you will see is the instrument panel. Now there is a favorite section there, and if you have been using the MRCT quite frequently, you will see the instrument appear under the favorite section. But if you don't see it over there, you can scroll down to transformer power factor test sets and click on MRCT there. This window comes up. Make sure that the use Ethernet option and auto discover unit is checked, and then click on OK. Then you see the forms. The recommended form is instrument transformer management software, which is what you'd be selecting to test instrument transformers. And then you're directed to this screen. You will click on the connect icon on the top left, and then this window appears where it shows you the unit that's plugged in right now. You will click on that unit. It shows you the serial number of the unit. So just click on that, and that connect icon should turn green to indicate that the instrument is now connected. So it's pretty straightforward. Now, where you may run into problems is I've seen some people use some other instruments with their laptop, and those instruments require them to assign an IP address manually. Now, if that is the setting on your laptop, then of course the laptop won't recognize the MRCT automatically because you have your laptop on manual setting. So you'll need to go into the network and sharing center on your laptop and change the properties on your Ethernet port to automatically detect the IP addresses so that it can easily communicate with the MRCT. If you want to leave it on manual, you can do that. There is a manual IP address associated with the MRCT as well, and you can enter that IP address and you should be able to communicate easily. So this is the home screen layout which you see when you connect to the instrument. Let's just go over this screen. On the top left, of course, the connect icon, which we just talked about, and then there's the settings icon, where we are going to go over the settings icon in the next slide. The nameplate section, where you would need to go to enter the nameplate data of the CT that you're about to test. Help, if you click on that question mark, you can see the user manual for the MRCT. So if you are out in the field, you need some help, you want to access the user manual and you don't have an electronic copy, you don't need to worry. You can just click on that question mark and you'll get access to the user manual. This is where it shows you what all testing functionalities are available on the MRCT. So if you have just the CT testing functionality, all the other options would be grayed out. If you have all of it available, you should be able to see all of these in the bar. Then here under the CT test screen, it shows you the individual tests that can be done on the CT. So you see ratio, saturation, winding resistance, insulation, burden. Demagnetization is not exactly a test, it's a process, but it's essential to this test sequence. So I'm going to include that here. What you will typically do is instead of going to individual test screens, you just click on run all tests and run the measurements from there. Besides that, you have a manual mode and you have a self-diagnostic mode. We are going to talk about each of these options. So let's start off by talking about the settings option. When you click on the settings icon, you can see all of these different things. Let's go over each of these points. So saturation standard is where you select the standard that would calculate that would determine what is the knee point voltage on the saturation curve. By default, it's set to ANSI 45, which means the knee point voltage is determined on the saturation curve by drawing a tangent, which makes an angle of 45 degrees with the horizontal. The point at which that tangent touches the curve is the knee point voltage. Color options is where you can change the colors of the traces for the saturation curve. Tolerance setting is where it shows you the limits, the tolerance limits for the ratio errors based on the standard that you have selected. Ratio error on primary current, it means that the measured ratio will be displayed based on your primary current. So let's say you're running a CT ratio test on a CT which has a ratio of 600 by 5. If you measure a CT ratio, you'll get a value like 600.2 by 5 instead of 600 by 4 point something. The ratio phase error table, what's the standard that's being used? It's set to ANSI over here. In the report and assessment section, you can decide what all contents you want to be displayed on the report. So if you click on report contents, you'll see all these different checkboxes, and you can pick and choose which ones you want to be displayed on the report. Asset owner, it's basically the style of the header that appears on the PowerDB test form. There are two options to choose from: asset owner or service company. If you are a utility, for example, you would stick to asset owner. If you're a testing company, you could switch to service company. Show connection diagrams, it's an important option. You need to make sure that it's set to show if you're new to the instrument. If you're not that comfortable with using the instrument, just leave it on show, or in general, just leave it on show. What that's going to do is it's going to bring up a connection diagram every time you try to run a test. And the connection diagram is a good way for you to verify that you have done everything right so far. You've made all the right connections. Knee prediction enabled allows you to specify the knee point voltage on the when you're running a saturation test. So for example, if you're running a C400, if you're running a saturation test on a C400 CT, you know that the knee point voltage should be somewhere close to 300 volts. You can just type in 300 volts, and based on the value that you enter, the software will speed up the increase in the voltage, and it will go close to 300 volts and then slow down because it expects the knee point to be around 300 volts. Or if you set it to auto find, the ramp rate is again going to be determined by the nameplate information that you put in the software. Leave it on enabled, but leave it on auto find so that you let the software base the ramp rate based on the nameplate information, and not manually enter a value. Leads check enabled. This is a nice function which the MRCT has, where it does some preliminary measurements before starting the actual test, and if it sees something wrong, then it shows you a message which says that you need to check your leads. So it's a nice feature to have enabled. Nameplate estimate, by default it's set to disable, and what it is if you're testing a CT which has a corroded nameplate, or if it doesn't have a nameplate, so you don't have any reference values, then in that case you can enable this, and based on the measurements that the test set gets, it will estimate the nameplate value based on that. Default number of taps is set to 5, and that's typically the case. You typically run into 5 tap CTs, right? So just leave it on that. Use binary input as stop. With this, you have a pair of binary contacts on the MRCT, and you can connect an external device and remotely stop the test by using this option. Default settings option is to restore defaults, update firmware. The firmware can be updated in 2 ways. You can either connect the instrument to the latest to your laptop and install the latest version of PowerDB on your laptop. And when you connect the MRCT to your laptop, you'll get a prompt which says that which asks you, which says that your MRCT doesn't have the latest version of firmware. Do you want to upgrade? And you say yes, and it runs you through the firmware upgrade process. That's one way of doing it. The other way is to actually get that firmware file. The file has an extension called LDR. You can get that file, put on a USB stick, put on your laptop, connect, direct the software to the exact location of the file, select the file, and it would manually upgrade the firmware. Display versions. Sometimes you may connect the connect icon may show that you're connected to the instrument, but if you still run into problems, you're not getting the measured values, it's not working right for you, then one way of verifying that the instrument is actually connected to your laptop is by coming here and making sure that you can see the information associated with the instrument. So you should be able to see the serial number, the firmware version, and everything. So it's one way. It's another way of verifying that your instrument has the latest firmware and that the laptop is actually communicating with the MRCT. Language is set to English. Primary noise filtration. So there is another feature which is there on the MRCT to remove noise and help you get better ratio errors. When you're out in the field testing a noisy environment, especially when you're trying to run a ratio test, it's very difficult to get good ratio error values because of the noise. The voltage that's typically induced in the primary is a very small value. It's a very low voltage. And so any noise that's present in the substation can cause interference. And one way of overcoming that noise or eliminating line frequency noise is by reversing the phase angle of the output voltage. And with this enabled, you do that, and so you eliminate line frequency noise. If you do not have a need for it, I would suggest that you keep it on disabled because enabling it reduces the accuracy by a little bit, not much, but we want it to be at its best accuracy wise. So let's just leave it on disabled. Show excitation curves as generated. When you run a saturation test with this option enabled, it will show you the curve in real time. So you'll see the curve being built as the values are being measured. If you want to speed up the test a little bit, you can go switch to the other option, which is quick test, where it runs the test first and then shows you the curves at the end. And that speeds up the process a little bit. You have the saturation demag method. If you get the DC testing option, then you can toggle between AC and DC. Communication, as I said earlier, is DHCP. It's auto detection, easy communication, but you can switch to manual mode too. Maximum AC test voltage is set at 2000 volts. There are some organizations which have a limit on the voltage which the instrument can be used at. So they do not want to exceed that limit. And to cater to those people, we provided a limit here where if you, let's say, you don't want to use the instrument at a voltage level above 1000 volts. In that case, you can put a limit of 1000 volts there. Fan speed percent, it relates to the speed of the fans that come on when the unit is operational or when the unit is heating up. Saturation curve ramp rate is set to 1. It's basically the ramp rate for the voltage when the saturation test is being done. And it's not just a simple number. The software bases it on the type of the CT that you're testing. For a protection CT is higher, for a metering CT it's lower, but you can influence the ramp rate too by changing that number. But I would suggest that just leave it on 1. Don't tinker with that. Let's come back to the home screen and now take a look at the nameplate icon. If you click on the nameplate icon, you will see this window. Let's go over each of these points. So on the top, you will see it says number of CTs. It says 1. If you're testing on an asset which has more than 1 CT, then it's possible for you to create a report or store multiple test results on the same file. So if you click on the number of CTs, if you click on 1, you get 18 options. So you can store up to 18 CT test results in one file, and we'll take a look at how to create a template for that in the next slide. Number of cores, if you are testing on a multi-core CT, then you can change that from 1 to whatever the number is. Number of tabs, by default, it's set to 5. If you're testing on a single tab CT, you can change it to 2. CT label, there are different options. There are 6 options to choose from: XYZ, UVW, I believe. Name, if it's not CT1, if it's CTA or something like that, you can change that too. So there's a lot of customization which can be done here in your report, and we've made it as user-friendly as possible. On the right here, you can enter the accuracy class and the burden specifications. You can select the type. You can select the accuracy class based on the type. So all of that information can be entered on the right, and on the left you can enter the reporting information like the manufacturer, serial number. If you have access to that, asset ID, it would be the ID that is provided to that CT, that is assigned to that CT by your organization. Phase is applicable to CTs which are mounted on an asset. So if you're testing a CT on a breaker and the CT is mounted on phase A of the breaker, then you would say phase A over there. Then you have a couple of checkboxes. One is for a buried CT in a delta connection. One is for a simulated primary lead swap. Let's talk about these 2 points later on. In service tab is the tab which would be in service, which would be used when a CT is in service. And then you can enter the ratios over here. You can add additional comments under user descriptions and values. You can specify the frequency of the output voltage by clicking on test frequency line. By default, it's set to line frequency. Let's go over manual mode. In the manual mode, you basically, as it suggests, the instrument is on manual mode, so you can only you will get this basic screen where it shows you the output voltage under X, so the voltage that's being put out by the X leads, the voltage that's being measured by the H leads, and the source current, the current that is coming out the X side will be displayed over there. You can ramp up the voltage by using the control knob. On the MRCT, you can change the ramp rate by using the arrow keys that you see over there. Self-diagnostic check is a basic, very basic way of making sure that the instrument is working fine. So if you start seeing weird values and you want to rule the instrument out as being a source of the problem, what you can do is you can click on the self-diagnostic option on the home screen. When you do that, it brings up a connection diagram where it shows you how to connect the leads. Basically, what you're doing is you're connecting the X leads to the H leads. The X1 lead connects to the H1 lead, and the X5 lead connects to the H2 lead. And you run the test. What it does is it applies voltage from the X side, and the H side measures that same voltage. So as long as that's the case, as long as it's measuring what it's putting out, then you know that the leads are functioning fine and the instrument also is functioning fine. So that kind of checks is a basic check for the instrument, and that's a very good thing that you good option to try out in case you're getting into in case you're getting weird values on while testing on CTs out on the side. So we talked about how it's possible to test multiple CTs on an asset and store all those results in one file. Right? Let's see how to go about doing that. So this is the nameplate window. What you will do is click on where it says number of CTs 1. So when you click on 1, you get a window where you get up to 18. So it's possible to store up to 18 CT test results in one file. I'm just going to pick the number 2 here. So you can see that 2 tabs appear there, CT1 and CT2. I'm going to start off by entering the nameplate information on CT1. Now, one good feature which is provided here is that you can copy the nameplate information from one CT to the other. Typically, when you test CTs mounted on an asset, you will see that there are more than one CTs which is similar to each other, and instead of spending time entering the nameplate information for each CT, what you can do is click on that copy from option which appears on the bottom right of the screen right here. You can click on that, and then it will ask you which CT do you want to copy the nameplate information from. I'm just going to pick CT1 here, and you can see that all of that information gets copied over. Now, if I want to tweak something, if I want to change the serial number, for example, I can do so, but I don't have to enter all that information all over again. Let's talk about the little checkbox that we saw earlier in the nameplate window. It says buried CT on a delta connection. So what do we mean by a buried CT? So when you're testing CTs on a transformer, you would see that CTs are typically present on the line of the winding. So they're mounted in that little space that exists in the bushing turret, and they're present on the line. But once in a while, you run into a CT on a delta winding, which is inside the delta winding before the line is formed. So instead of lying somewhere over here, the CT would be over here inside the delta. So when you have to test this CT, the way it's different in this case is the CT, because it lies inside the closed, inside the delta, it's basically present inside a closed loop with the three windings. To test this CT, what you will do is you'll connect your primary leads. The H1 lead will go on the side on which the CT is, and the H2 lead will go on the other side. And when you run this test, what happens is you apply voltage on the CT secondary, and a certain voltage is induced on the CT primary. And that voltage, that little bit of voltage that's induced in the primary, is now in series with three impedances. So it's a closed circuit with a voltage source and three impedances in circuit. Now what happens is that voltage that's induced here, it drops along these three impedances in equal amounts, right? So 1/3 of the voltage will appear here, 1/3 of the voltage appears here, 1/3 of the voltage appears here. What we are doing is we are measuring the voltage drop between these 2 points. So what we get is V2 minus 1/3 of V2. So we end up measuring 2/3 of V2. But to be able to measure the CT ratio, what we want to measure is we want to measure V2, but it's not possible because of this situation. So what we end up measuring is a ratio which is 3/2 times the actual ratio. So the ratio error that you would see would be a high value. You typically see a ratio error of 50% when you're trying to test a buried CT. So the way to overcome this problem is check that box. So the software applies a correction factor, a multiplier that compensates for that 2/3 that we see here, and with that you get the correct ratio values. Using simulated primary lead swap. So let's say you're testing on an asset which has a CT on either side, and the polarity is as shown here. To test CT1, you're going to connect the primary leads in this manner. The H1 goes on the side on which the CT1 is, H2 goes on the opposite side. And let's say the red box is breaker, the breaker is closed, and you run the test. You will get the values for CT1. Now, if you have to move on to CT2, you can simulate a primary lead swap instead of having to physically swap the leads by checking this box. When you check this box, it simulates the lead swap, and you can run the test without physically moving H1 to CT2 side and moving H2 to the other side. Now, the situation in which this is really useful is where you are testing on an asset and it's not possible to disconnect the ground from the primary side. Or let's say if you're testing, let's say if you are testing on this particular asset, and let's say this point is grounded, you can test CT1 because H1 is grounded by the instrument, right? But when you try to test CT2, now if you try to swap the leads, your H1 is grounded by the instrument at this point, but there is a permanent ground provided over here. So you essentially have a short circuit where both points are grounded. It's not possible for you to run the test. So in cases like those, it's easier for you, or the practical way, or the only way possible is for you to simulate a primary lead swap to where you make sure that you do not have grounds on both sides, and you also end up testing the CT without getting a reverse polarity on your report. Testing CTs mounted on a transformer. Typically, when you're on the field and trying to test CTs which are mounted on a transformer, you will see a high ratio error, and it's pretty common for us to get calls where you have a customer who is out in the field and trying to test CTs and running into high ratio errors. So, and that's why I chose to include this slide in the presentation. So let's say we are testing a CT which is present on the high side winding. Let's say the high side winding is a delta, and we are trying to test this particular CT. What we will do is to test this CT, if we are getting high ratio errors, what we'll do is we'll start off by shorting the low voltage winding. So if you're testing CTs on the high side winding, short the low voltage winding bushings, and then run a measurement. If you are still getting high ratio errors, what you can do is you can short the other two bushings on the high side. On the high side, your primary leads, the H1 primary lead will be connected on this particular bushing. The H2 lead will be connected on either of these bushings. It doesn't matter, but you will short the other two bushings, and that way you will end up getting better ratio error values. So the ratio error should come down to within acceptable limits if you do this. So why exactly do we do this? When we are testing CTs mounted on a transformer, the CT primary is in series with the winding itself, right? So the winding has an impedance, and that impedance is pretty high if the transformer is an open circuit. If the transformer is an open circuit, then that impedance is the excitation impedance of the transformer, and that is a very high number. So what we do is by shorting the low voltage winding, we put a short across the excitation impedance, and what we get is the leakage impedance, which is a much smaller number than the excitation impedance. So that brings the impedance value down, and that enables the instrument to get accurate values. When we short the other two bushings, that further reduces the impedance value, and so it makes it that much more easier for the instrument to give us accurate results. So that's the logic behind shorting those bushings on the primary. Now let's talk about the testing part itself. Having covered all these other points in the software, let's talk about the testing bit. So when you try to run the test, you will see this connection diagram. Again, this is important. It's important that you in the settings you set it to show connection diagram so that you see this diagram every time you run a test. And here for CT testing, it shows you that you will need to use the secondary leads, you'll need to use the primary leads, and the connections need to be done in this way. The pictures of the leads are shown on the right here. So the one on the top here is the primary lead. You will see a pair of stress relievers on the primary leads. These are used to make sure that the clamp doesn't slip from the bushing under the weight of the cable. So what you will do is you'll wrap the cable once around the bushing and run it through that stress reliever, so that takes the pressure off of the connection. On the secondary cable, this is what it looks like. One side has 7 connections, the other side has 5 connections on the standard leads, and the side that goes on the CT it's a banana connection, so it can be used with spade lugs, it can be used with dolphin clips, injection clips. Provide all these options, and based on what you like, you can pick one and use that. So that's the connection diagram. Now let's actually see what happens when we try to run the test. Okay, so let's say I have a CT and I have to run all of these tests. I'm not going to test the burden. Not going to run the burden test here because that test doesn't involve the CT itself. The test sequence is going to involve all the other tests. So I'll start off by clicking on nameplate, and it brings up this nameplate window, and I'll enter whatever information I can find on the nameplate of the CT over here. Once I have entered all of this information, I will click on the check mark, and then click on Run All Tests. When I click on Run All Tests, it brings up this window where it shows me all these different checkboxes for different combinations. Now, the thing with the MRCT is you can you do concurrent testing over here, which means that in a single measurement, you take the measurements across all these different tap combinations, so you do not have to repeat the same test again, and that reduces the testing time by a lot. So that's one of the main advantages of using the MRCT. Once I'm done selecting my tests, I hit the play button, brings up the connection diagram. I get past that, it starts the test sequence. It starts off by doing the insulation resistance test. I just selected one measurement, primary to secondary, and that's being done at 500 volts. There are two options to choose from, 500 volts or 1 kV. It says here greater than 10 gigaohms. 10 gigaohms is the range of the insulation resistance test circuit. So if it's greater than that, it's just going to give you a greater than sign, and that's sufficient for us. Then it starts off with the winding resistance test, where it injects a certain DC current through the winding. Here it's injecting a 0.5 amp, and you can see the voltage drops being measured at different points. Based on the voltage drops that it measures, V by I, it gives you the resistance of the winding at different points, across different points. And after that, it does the demagnetization test, where it over excites the CT core and then gradually brings the excitation level back down to 0. So that way it restores the core back to its original state. All that remnant flux is removed. What you see here is a pictorial representation, a symbolic representation of what's going on there. It shows you a BH loop for the core, and you will see that the loop is decreasing in size. Now, this process is very essential to the test sequence, and it also takes up the longest time in this sequence. An MRCT can test a CT in 5 to 7 minutes, depending on the type of the CT. But out of those 5 to 7 minutes, 2 minutes are taken up by the demagnetization process. Once the demag is complete, it moves on to the saturation test, where it applies a voltage across the secondary winding and it measures the excitation current. And as you can see, the curves are being built. You can see that the response is linear. On the x-axis, you have the current. On the y-axis, you have the voltage. And it increases linearly until the core starts to approach saturation. And what you see is the curves start to flatten out. At that point, we say that we know that the saturation has been achieved, and the software uses the saturation standard to compute the knee point voltage, and the knee point voltage is shown as an asterisk mark on the graph. So you'll see all these marks appear, and what we are interested in is the outermost saturation curve, which is for X1 to X5 for the whole winding of the CT. And you'll see that the mark appears somewhere close to 27 volts. Once it's done with the saturation test, it does the ratio test. It doesn't ask you for a test voltage. It automatically applies a test voltage based on the values that it sees during the saturation test. So in this case, the test is being done at 21 volts. And you can see the primary voltage that's induced, such a small number, it's 0.18 volts. Once the test is complete, it drops the voltage back down to 0. And that is the last test. At the end of the ratio test, you get this report. The report is a 2-page report based on the contents that you want to see, and we will cover the report in the next slide. So it's pretty easy to use, pretty intuitive. When you're about to test a CT, what you do is click on the nameplate section, enter the nameplate section, create the template, and then move back to the home screen, click on Run All Tests, pick the test that you want to run, and then hit the play button, and the instrument will take care of the rest. At the end, when the report is generated, you can save it as an XML file, or you can even save it as a PDF. You can see this option, Save to PDF. If you want to send it to someone who doesn't have PowerDB on their laptop, they would still be able to see the report. So let's go over this report. The first section includes the nameplate data. So whatever information you enter in the nameplate window appears there. If you forgot to enter something, or if you would like to enter something later on, it's possible to do that. And then under that, you have the measurements table where it has the ratio values for all taps. It has the knee point values for all taps. For the CT winding, for the whole winding, the saturation voltage is at 27 volts. The phase deviation is 360 degrees or 0 degrees, which means that the polarity is correct. The polarity would have read reverse if the phase deviation was 180 degrees. The resistance values are shown in the last column, and then right here you have the insulation resistance value. Under this, you have the saturation curve for all these combinations, and there's a little checkbox here which says display saturation test data. If you click on that, you get all of the data points that were measured in this test in a tabular format. Under that, you have the assessment portion on page 2, and what it shows you is the magnitude of the ratio error and the phase displacement of the ratio error at different levels of current. Now you will see here that the current level ranges from 1% to all the way up to 200%. So we did not inject any current in this test. How did we end up measuring all these ratio errors? So on this page, whatever values you see, these values have been determined from calculation. So these are not measurements, but these are calculations based on the measurements that we have done. And what it is you have these different levels of current, and you have these different burdens, right? And these burdens are based these values are based on this circuit. So this circuit is something that we saw earlier when we were talking about CTs. You have a primary here, and that primary current results in the formation in the production of secondary current. But there are two branches here. One branch is the excitation current. The other branch is the branch which connects the external burden, and the current that flows through that burden is the actual current that we measure out of the CT. Now the ratio error that we get when the CT is under operation and it's operating at different levels of current is basically due to the excitation current that's being utilized in the excitation of the core. And what we did was, when we did the saturation test, we measured that excitation current for different levels of voltage, right? So when a certain current flows through a certain burden, the voltage that develops across the secondary terminals is current times that burden. So we have the values of current here, we have the values of the burden here. So current times burden gives us the secondary terminal voltage, and from the saturation curve we determine what is the excitation current which would flow through this branch for that particular secondary terminal voltage, and from that excitation current we determine what is the percentage ratio error. And we don't just look at the magnitude, we also look at the phase displacement, and all of these values are calculated based on the measurements done earlier and shown here in a tabular format. We can also see this in a graphical format where it shows how the ratio error changes magnitude wise and phase displacement wise as the current is increased. So based on these, we provide a final summary of the assessment where we say that this is the ratio error calculated at 20 times the rated current. In this case, it's 0.18%, and if you recall, we said that the error limit for a protection CT is 10%. So it's much well within the error limit that's specified, and the ratio error that we actually measured when we ran the test, when we applied the voltage on the secondary side, is 0.0981%. When it says pass for the class, it means that the CT satisfies the class requirements for a C20 CT. So that was a little bit about the report. Now let's look at the icons. For those of you who have the MRCT with the onboard display, you may have seen some of these icons. Let me just go over what these icons mean. So the folder with the arrow pointing out of it is the open file. If you select a file and then click on this, that will open up that test file. The folder with the arrow pointing inside it is the save file option. So if you select a file and then click on this, and you'll be able to save the file. Transfer to USB with the arrow pointing towards the USB. arrow pointing away from the USB is transfer from USB. So it's possible for you to transfer the data from the MRCT to a USB stick, and that's the way that way you would be able to read the results on your laptop. On the other hand, if you want to put some results on the MRCT, it's possible for you to do that by using the transfer from USB options. When you plug in a USB stick into your MRCT, you would be able to see whatever content is in there, whatever PowerDB files are in the USB stick over here, and then you can copy to or copy from based on your requirement. You can delete files by clicking on the delete option. You can close out of this window by clicking on the close option, and then you have these scroll keys to scroll between files. So that was about the MRCT with regards to CT testing. Let's talk a little bit about the added functionalities that we have on the MRCT, and that is to be able to test VTs and CVTs. So what are VTs? VTs are inductive voltage transformers, electromagnetic type transformers, which is basically a transformer, but the main difference is that it has a low power rating. So you cannot power a load off of it. You can power small loads like metering loads, protection circuits, but not big loads. What you will see is physically you will see two types of arrangements. There's a dual bushing type where that you might see that in low voltage applications where there are two bushings and the VT can be used for line-to-line measurement. But typically what you see is in high voltage applications, you see a single bushing arrangement where you have a single bushing which is meant to be connected on the line side, and then you have a ground terminal. On the secondary winding, you may have one or more secondaries. One secondary would be for metering purposes, one secondary would be for protection purposes. What it shows you here is the burden. So if you look in the nameplate, you may see this designation. You may see W or a Y or a Z. What does that mean? So W, for example, means that this is the burden associated with it, based on whether the secondary winding is a 120 volt winding or a 69 volt winding. Okay, so those letters signify, they tell you about the burden that it's suitable for. Capacitive voltage transformers, or CVTs, CVTs, coupling capacitive voltage transformers, these are all used for the same instrument, that is a capacitive voltage transformer. And the way it differs from a conventional inductive voltage transformer is it has a capacitive voltage divider in series with the electromagnetic type component. So this is the simplified circuit for a CVT. So you have a capacitive divider network. So what happens is when the CVT is connected in the system, the voltage that appears between the line and ground gets divided amongst these capacitor elements, and one of the capacitor and the lowermost capacitor element is connected to the EMU, the electromagnetic unit, and the voltage is further stepped down to 120 volts or 69 volts. There is a tuning reactor in series here, which takes care of ferroresonance conditions. So there are different ways in which it differs from a conventional inductive voltage transformer. But what you will typically see is when we go to high voltage levels like 345 kV or above, you will see CVTs being used everywhere instead of inductive voltage transformer. And that's because when you go to those high voltage levels, it costs less and it's more economical to manufacture CVTs for that application than inductive voltage transformers. Where they differ is they differ in the transient response because of the storage elements like capacitors which are present in the circuit. They may not be the response to a transient may not be as quick. They're impervious to ferroresonance. Ferroresonance is a condition in which the inductance of the VT becomes in parallel with the capacitance that exists in the network, and in high voltage conditions which may arise because of switching surges, there may be ferroresonance which can result in a high amount of current flowing through the winding of the PT. And as I said, these are low power rating instruments, and that can easily damage the windings of the VTs. CVT is not so much. They operate at a low flux density, so they're more or less resistant to they do not get affected by ferroresonance as much. So let's talk about testing VTs with an MRCT. So these are the leads that you would need. If you get the VT testing option, you want to make sure that you get the leads as well along with it. If you look at the lead that is provided over here, this is the primary lead which is used in CT testing. So you should already have this. When you get the VT testing option, you should get these two additional leads. One is red blue, one is red black. What you will see in the diagram is the primary lead goes from the MRCT, from H1, H2 on the MRCT to X1, X2 on the PT. So on the secondary winding of the PT. And if you look at the polarity, you will see that it's different when you're testing a VT. So the H1, the black lead goes from H1 on the MRCT to X2 on the MRCT. The red lead goes from H2 to X1. Okay, so make sure that the polarity is or the connections are being done exactly as shown in the connection diagram. And then you have these primary leads. The red blue goes on H1 from X5. The red black goes from X1 to H0, which is the grounded terminal. So make the connections. We have tried to make it as easy, as user-friendly as possible. These are all color-coded. There are labels provided. There's a connection diagram. So make sure that you make the connections in the right manner. So let's see what let's do a ratio test on a VT and see what it looks like on the software. So I'll do the same thing. I'll click on nameplate. That brings up the nameplate window. I will enter whatever information I can find on the nameplate of the VT. So I entered the accuracy class, the burden information. I entered the primary voltage and the secondary voltage. I want to make sure that I put in phase to ground or a line to line there, depending on what's the case. And then I click on the ratio test. Since I'm just going to be running the ratio test, I won't be clicking on run all test option, and that brings up the connection diagram. This is the same diagram as what we saw earlier. It's accompanied with a warning which says make sure that you test it, make sure that you make the connections in the right manner. So I'm going to hit the play button, and that's going to start the test. So the ratio test for a VT is done at about 300 volts. It's the same test as what we see on the CT. For a VT though, the voltage is applied on the primary side, which is why we connect the X leads to the primary winding. And we measure the voltage induced on the primary side, on the secondary side. So you can see that the instrument is applying around 290 volts on the primary, on the primary of the VT, and we are getting the secondary, we are getting some voltage on the secondary winding. And based on the voltages, it measures the value, and we get this table where it shows us the magnitude of the ratio error, it shows the phase deviation, and then it generates a report. So this is what the report looks like. Let's take a look at it. We entered some nameplate information in there, so that's already provided there. Again, if you want to enter something else, we can enter that later too. And then the ratio data is provided in this table. We can see the nameplate value, we can see the measured value, we can see the magnitude, the test voltage, the measured voltage, phase deviation, polarity. So all of that information is provided there. If your secondary winding had more than one tap, so if it had X1, X2, X3, it's possible for you to create a template for that as well. So you would have two taps here, X1 to X2, X1 to X3, and you would have the ratios associated with those. So we won't be covering the other advanced tests in this video. I'm just gonna keep things short. You know how to do it. I mean, the process would be the same for each test. Make sure that you make the connections as per the connection diagram, and the software takes care of the rest. Let's talk about a CVT now. The way the CVT differs is you need a special lead, and the testing option is different. So if you have the VT testing option, doesn't mean that you can test a CVT with it. When you get the CVT testing option, you get this lead that's shown here on the right. This is a special lead that comes for CVT testing, and you will see that there is an additional ground connection provided here that ground connection, if you look at the connection diagram, goes on the ground terminal here, along with the ground that is there on the primary leads, on the H1, H2 primary leads. So you will be using these three leads, the CVT primary lead and the original primary lead that we have been using all along. We use this in the CT testing, we use this in the VT testing as well. And we use the red and black lead. The red and black lead goes on the grounded terminal as it did when we tested a VT with it, right? So the red and black terminal runs from X1 on the MRCT to H0 on the CVT. The primary lead runs from H1, H2 to X2, X1 on the CVT secondary winding. The CVT primary lead runs from X5 on the MRCT to H1 on the CVT. Let's try to run a test and see what happens. So the process is the same. You enter the nameplate information in the nameplate window. So you would enter the burden information, the primary voltage and the secondary voltage. Based on the primary and the secondary voltage, it shows you the nameplate ratio, verify that that's correct, and then click on the ratio option to start off with the ratio test. When you hit the play button, it brings up the connection diagram. Again, verify that the connections are good, are done as per the diagram, and then when you hit the play button, it starts the measurement. The measurement screen is again the same. It applies a voltage on the primary side of the CVT. Because of the capacitor divider network and because of it being such a having such a high ratio, you need to go high on the voltage, which is why it's different from an inductive voltage testing option. People who get a VT testing option may not be able to accurately test CVT ratios. So what you do is, what the tester does, it applies a voltage of 2 kV to measure the ratio. And of course, you will see that the rise in voltage is gradual, and it runs multiple measurements and make sure that it's as accurate as possible. The accuracy of these measurements is really important, which is why we provide it as a separate testing option. The VT testing option is field upgradable. So if you have a unit, if you have a new unit which you purchase just to be able to test CTs, and you want to later on add a VT testing option, you can do so without having to send the unit back into the factory. But for a CVT testing, for you to be able to include the CVT testing option, it does need to be sent in because some additional calibration procedures need to be performed for it to be accurately able to measure the CT ratio at that level. So once it records the measurement, it brings the voltage back down. Now here you can see that the percentage ratio error is a high number. And the reason why it's a high number is because when you're testing out there on a CVT, the way it differs from an inductive voltage transformer is you will see a grounding switch on the voltage tab on the CVT. Now those grounding switches need to be opened for you to be able to get a proper result. If you do not do that, then this is what you get. The ratio errors will be high, and at that point you need to go over to the secondary, to where the secondary is, and make sure that the grounding switches have been opened. Now this is what the report looks like. Again, it's the same format as what you see earlier. There's a nameplate section and there is a table here. This is the result for from a test which was done properly, and you can see that the percentage error is within limits 0.14%, and the test voltage is 2 kV. The phase deviation is also shown there. So this is the type of report that you get when you test on a CVT. So that concludes my presentation. We started off by talking about CT, then we talked about CT testing, then we talked about testing CTs with the MRCT, then we moved on to testing VTs and CVTs. If you have any questions, of course, we'll be answering those right now, but if you want to reach out to me, you can do so. That's my email address. Thanks. Over to you, Mike.
Thanks, Sanket. So now that we've finished our presentation portion of the webinar, we'll jump into the Q&A session where we're going to try and answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's also a field where you can request a quote or a demo of any Megger products. A copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars as well as register for our upcoming webinars on our website at us.megger.com/webinars and register for our virtual cable best practices seminar on Monday, August 10th. All right, so let's jump into your questions. The first one I'm going to direct over to Volny Naranjo. Volny, can the MRCT show the modified saturation curve of the CT if the transformer curve is saturated?
Okay, Michael, thank you. I'm not sure about the full extent of the question. The way I'm seeing it is that if a CT has an issue or has a problem in the magnetic core in the magnetics or the core of the CT, or for example it is magnetized, or let's say there was a fault and the CT is saturated, fully saturated, or there's any problem in the winding, and the curve, the saturation curve, is not gonna show correct, or is gonna be like not a failing test. The saturation curve is gonna show deformated. A regular saturation curve has to have a linear section. Sanket showed a couple of slides where you see actually one from the IEEE where you have the linear section, and then it has the knee point, and then it has the saturated section. So after that knee point. So if there's any problem in the CT, you're going to see that especially that linear curve, that linear section of the curve is not going to be linear at all, or it's going to be too short, and the saturation point is going to be reached, or the knee point is going to be reached very early in the voltage increments. So if that is the way you would see the results in the graph, that they are not matching exactly the saturation curve that you're expecting from the manufacturer, and that is the way to compare to, or to analyze the saturation curve or the excitation curve. You compare to the manufacturer supplied curve, and if it doesn't match, then you have to investigate. And in that same graph, you can see the one from the IEEE. You have some limits, and you can determine if the saturation curve is satisfactory or not from there.
All right, thank you, Volny. Our second question I'll be sending to Daniel Carreño. Daniel, can you talk about the CT nameplate and the information we're looking for on it?
Sure, Michael. Hello, everybody. Well, Sanket for sure covered a little bit of the nameplate information you fill out in the software when you're performing the test. So Sanket, I don't know if you can go back to slide 27. That's where you have the screenshot for that screen, so it will be useful to use while we talk about this. So for sure you have identification information, right? You want to have that in the report, so the report looks nice, and it has all the information about the CT under test. And also, first, very important is the classification of the CT, right? First, you tell the software that you are testing a meter type or a protection type. So I can cover that initially in the presentation. And then what is the accuracy class for the CT? It is important that you guys fill out that information in the nameplate, so the software will help you with the assessment of the results, right? Once you get the measurement data, if you do have that information filled out in the software, again, the software has a great feature called a CT assessment or nameplate assessment. And again, the software can analyze the results based on the information you provide in the nameplate, and of course the ratios, right? You want to fill out the ratios for the CT under test, and again, so the software can help you with the assessment of the results, showing the error, right? The percentage error of the ratio is how we analyze, how we decide if the results are good or bad. So again, if you don't fill out this information, then the software it won't calculate the errors on that part. Now, remember as well, and Sanket mentioned that the software has another great feature called nameplate estimation. You can actually go right into testing without filling out the nameplate, and the software, as soon as it finishes the measurements, it will try to match the results of the CT under test to a known nameplate. And just as when you use it in the software, you will get a message. As soon as you enable that option, you will get a warning. You should be aware that by no means you should, or we're encouraging that nobody fills out the nameplate. It's just an added feature for helping the user. But you always, if you do have the information, it's good that if you use the estimation, you double check the results of the matched nameplate that the software found to the actual nameplate for the CT under test.
All right, thank you, Daniel. While we have you, regarding the connection on slide 17 for IR test, the connection diagram is touching the ground. Is that okay since the IR should be between primary and secondary only?
Yes, okay, and Sanket, if you can again help us going back to that slide. I think I know what this question is referring to. I think it's slide 17, yes.
Slide 70, yep, 17.
Yes, so when we perform insulation resistance, different measurements reported. CT secondary to ground, CT primary to ground, and CT secondary to primary. So this actual connection, the unit will do it for you. So when you're, just as in the diagram that Sanket is showing, you notice the primary of the CT is shorted, and then the source that you use for the test is connected between the primary and the ground point, which is shorted to the secondary. So right in this diagram, we're testing primary to ground. Why do we do the test like that? It's just easier for troubleshooting. In the case that you get a lower number, right, some unexpected result, it's easier for you to pinpoint where the problem is, either in the primary side insulation or the secondary side, and so on. So again, it will make easier for you to troubleshoot in case you get any unexpected result, and the unit will do the grounding for you.
All right, thank you. Volney, could you please explain in more detail the DC technique for CT saturation tests on CTs with knee points up to 30 kV?
Okay, good, interesting question, because definitely those CTs are out there, and they're common in generating facilities. And when you use the conventional or the traditional method of applying voltage to saturate or to reach that knee point, then you would need, if the knee point is that high, around 30 kV or anything above 2 kV, which is the standard voltage of CT testing equipment, then you're going to be limited because you cannot reach that voltage. So, standards like IEC, they also explain, or they have another method to perform this excitation curve. And when we are doing the excitation curve, the idea is to generate the amount of flux necessary to of course generate the induction, or have the induction on the CT. And at certain point, it is going to be reached in these voltage that we increase. when you do the integral of that voltage, that is when you get a measure of, or you get a calculation of the flux that is produced, and when you do that, you can get the saturation curve. So that's why applying voltage, you can get to that point. Now, if you when you apply an AC voltage, you are increasing voltage gradually. And well, another way to generate flux in a CT is by applying DC current and maintaining that DC current for a period of time. So instead of changing time, instead of changing voltage, you are increasing time of the applied voltage and of the induced voltage or induced current that you are putting there, and then calculating the integral of that DC curve, it gives you the same amount of flux. So it's an alternate method by applying DC signal excitation, and then you can do, by mathematical conversion or transforms, you can determine the saturation point. It's a method that it's explained in IC 600-44-6, and it's something that it's implemented in the MRCT, and also another product that we have, which is the MVCT.
All right, thank you, Volney. Daniel, assuming the nameplate of the CT is not available, can we identify whether the CT is metering or a protection type?
Sure, and this, I should have explained this in my previous answer to the question on the nameplate. So yes, when you're using the nameplate estimation feature, you don't even have to tell the software the CT is metering or protection. The software will identify that for you. But again, I should emphasize, double check the results in the report if you're using the nameplate estimation.
All right, thank you. Volney, could you please explain a bit further the calculation of the knee point, because a 45-degree slope changes depending upon the scale. So I was told that the knee point is the point where the slope is 1/5 that of the initial slope.
Okay, so the 45-degree or 30-degree tangent method, these are methods that are described in IEEE C5713, and these are these 45-degree and 30-degree methods were established from experience using conventional magnetic materials, and the significance of these tangent points will be dependent on the magnetic material in use. That is actually, I'm reading a note from the standard, and the idea is that well, if you are testing if the CT is manufactured to that standard, it should comply with that. And the manufacturer, when they manufacture the CT, they will verify these. That's actually why they are called class, or the class has a letter at the beginning, which is C or T, and C means that it's calculated, T means that it's tested, and they had to verify that because of the materials they're using. There are other methods. I see, actually, if I'm not wrong, or if I'm remembering correctly, they established a knee point at the point where you an increase of 10% in voltage. As you are increasing voltage to get this curve, you are doing increase of let's say 10% values, and at the moment that 10% increase generates or produces a 50% increase or change in the current, excitation current, then that is where you it is declared the knee point of the CT. This is the method that IC standard uses. The other thing to mention, which is indicated in the question, is that it depends on the scale. Well, as per IEEE, this excitation curve has to be shown in a log coordinates, so both coordinates or both axes have to be in logarithmic scale, and the decades have to be in squares. So I don't know, the 1/5 relation. I've never heard of that one, but I just mentioned the two methods that are available. The most common methods are the IEEE and the IC. I hope that answers the question.
All right, thank you, Volney. And thank you all for joining us, including our panelists and presenter, and especially you, our audience. Unfortunately, it looks like that's all the time we have for today. We went a little bit over time. We apologize if we didn't get to your question online, but we will be following up with you offline in the following week. As a reminder, a copy of the presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will also include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all for attending, and I hope you all have a great weekend.